Welcome to our universe. Tonight, we cross a threshold that most maps won't show you, into the true scale of things, where the galaxy you live in becomes almost too small to mark, and the distances fold into something closer to silence than to number. We'll move from the faint spiral arms of home through the structures that hold it, layer by layer, until what felt vast becomes a footnote. If this feels like your kind of place, subscribe. Every person who finds their way here makes this universe a little more ours, because this universe has always been too vast to be anything but ours. Let's begin. The Milky Way is enormous until you leave it. Imagine standing somewhere in a wheat field on a moonless night. You look up, the sky is thick with stars, so many it looks like someone tore open the dark and left the light on underneath. You can feel the breadth of it, the arc overhead from one horizon to the other, and the faint luminous smear cutting across the middle. That smear is the Milky Way. You are inside it, looking at it edge-on from within, the way you might look at a piece of glass held sideways, seeing the whole thickness compressed into a line. 100 billion stars, maybe 400 billion. Scientists aren't certain. The ones buried in the dust behind the galactic core are still uncounted, screened behind interstellar clouds that visible light cannot penetrate. The disk stretches roughly 100,000 light-years across. More recent measurements suggest the outer spiral arms extend to perhaps 200,000, a number that stops meaning anything within seconds of hearing it. But here is what that number actually is. Light. 300,000 kilometers every second, the fastest thing in the universe, takes 100,000 years to cross the Milky Way from edge to edge. Maybe 200,000 if the outer rim measurements are right. The entire span of recorded human civilization, from the first cuneiform tablets to this moment, covers roughly 6,000 years. Inside the time it takes light to cross the galaxy, you could fit that civilization's full length more than 16,000 times over. Not 30, not 100, 16,000. You could spend the entire arc of recorded human history watching light move, and it would cover barely a fraction of the crossing. And that is the galaxy we live in, not the universe, the galaxy. Now step back. The observable universe, the sphere from which light has had time to reach us since the Big Bang, spans 93 billion light-years. The Milky Way represents approximately 0.000011% of that diameter. If the observable universe were the size of North America, the Milky Way would be a small coin on a table somewhere in the middle of Ohio. Not a large coin, the smallest denomination in circulation. And on that same map, the solar system, the sun and all its planets would be smaller than an atom. The wheat field, the moonless night, all 400 billion stars overhead, they fit in the space a thumbnail covers. This is where we live. This is home. And we are just beginning to understand how small it is. A light year holds more distance than anything has crossed. A light year is roughly 9.46 trillion kilometers, about 5.88 trillion miles. The number is decorative at human scale. It doesn't carry weight until you place it beside something it dwarfs completely. Consider Voyager 1, launched in September 1977 It is currently the most distant human-made object in existence. It has been traveling for nearly half a century. It moves at approximately 17 kilometers per second, faster than any bullet, faster than almost anything we have ever built. At that pace, it has covered roughly 24 billion kilometers since launch. 1 light year is 9,460 billion kilometers. After merely 50 years of continuous travel, Voyager has covered about 1/4% of 1 light year. 1/4% of 1. The nearest star to our Sun, Proxima Centauri, is 4.24 light years away. At Voyager's current speed, reaching Proxima Centauri would take approximately 73,000 years. Not from now, 73,000 years from the moment it was launched, meaning it would arrive roughly 73,000 years after 1977. The Milky Way's diameter, 100,000 light years. The Andromeda Galaxy, nearest major neighbor, 2.537 million light years. The edge of the local group, roughly 5 million light years. The Virgo cluster, our gravitational neighborhood's hub, 65 million light years. Laniakea, the supercluster we belong to, 520 million light years. The observable universe, 93 billion light years. These are not similar numbers. They are not in the same category of magnitude. The gap between Proxima Centauri and the edge of the observable universe is as incomprehensible as the gap between a single heartbeat and the age of the cosmos. Every distance we talk about tonight will be built from these numbers. They don't get smaller, they only grow. The Sun has orbited the Milky Way only 20 times. Our solar system is about 4.5 billion years old. The Milky Way rotates, not like a rigid disk. It rotates differentially, the inner arms moving faster than the outer ones. Stars constantly changing neighbors over deep time. The whole structure slowly churning like a vast, slow whirlpool. The Sun, sitting roughly 26,000 light years from the galactic center, takes between 225 and 250 million years to complete one full orbit of the galaxy. That span of time has a name, a cosmic year, a galactic year. The Sun has completed this journey approximately 20 times since it formed. The last time the Sun occupied this exact position in its circuit around the galaxy, the Triassic had just ended and the first dinosaurs were appearing. The time before that, complex multicellular life had only recently diversified. Go back 10 orbits, and Earth itself was still less than 1 billion years old, a young, volcanically violent world with almost no oxygen in its atmosphere. 20 orbits. That is the age of the solar system in galactic years. Now consider, the observable universe is approximately 13.8 billion years old. At 225 million years per cosmic year, that gives the universe an age of about 60 cosmic years. 60 galactic years from the Big Bang to now. 60 laps around the galactic center in the currency of the Sun's orbit. At that pace, you could set a clock, not ticking seconds, but ticking cosmic years, and hear it ring 60 times across the entire age of everything we can observe. The Big Bang at ring 0. The formation of the first stars around ring 1. The Milky Way itself assembling around ring 40. Our solar system forming around ring 55. 60 rings. and the Sun, after 20 orbits of its own, finds itself in a galaxy that is still middle-aged, in a universe that has barely begun. IC 1101 contains 100 trillion stars. In the constellation Virgo, approximately 1 billion light-years from here, there is a galaxy called IC 1101. It is the largest galaxy astronomers have so far found. IC 1101 spans somewhere between 4 million and 6 million light-years in diameter. Not length, diameter. It is an elliptical galaxy. No spiral arms, no dramatic disk structure, just an immense, slowly dimming sphere of old stars that have long since passed their brightest burning. At its center sits one of the most massive black holes ever measured. The galaxy is thought to contain approximately 100 trillion stars. The Milky Way, at the high end of estimates, contains around 400 billion stars and stretches roughly 100,000 to 200,000 light-years wide. IC 1101 is roughly 40 times larger in diameter. Some measurements suggest 60 times. In terms of star count, it contains somewhere between 250 and 1,000 times as many stars as the Milky Way. There is no comfortable way to hold this comparison. Our galaxy, which took human civilization centuries to even understand was a galaxy, which looked to the naked eye like nothing more than a band of light, which the ancient Greeks assumed was milk spilled across the heavens, is a rounding error beside IC 1101. And IC 1101 is not at the edge of what we can observe. It is not particularly distant by cosmological standards. It is simply the largest we have so far found, in a universe of at minimum 2 trillion galaxies across a volume we have only begun to survey. If the estimate of 2 trillion galaxies is revised upward again, as it was revised upward by a factor of 10 in 2016, there may be 20 trillion. In a universe that large and that old, IC 1101 may not be exceptional. It may be ordinary. We simply cannot yet see far enough to know. The Milky Way fills 1 part in 100 million billion of observable space. Some numbers don't land until you write them slowly. The observable universe has a volume of approximately 4 times 10 to the 80 power cubic meters. The Milky Way has a volume of approximately 3.3 times 10 to the 61 power cubic meters. The ratio: the Milky Way occupies about 10 to the minus 19 of the observable universe's volume, a tenth of a quintillionth. Put another way, if you filled the observable universe with Milky Way galaxies stacked and packed without gaps, you could fit roughly 100 million billion of them inside. 100 million billion. Let that settle for a moment. The Milky Way is not small by any measure that touches daily human experience. It contains everything we have ever looked at with our naked eyes from the surface of Earth. Every constellation, every navigation star, every planet named for a god, every story told about the sky from any culture, in any era of human history, all of it drawn from inside one galaxy that is 0.000000001 of the observable volume. Not small, not by any human measure, and yet invisibly, absurdly, humblingly small. The scale of the universe does not care about the scale of human experience. It was built at a different register entirely. Something enormous pulls everything we know in one direction. The Milky Way is not sitting still. Nothing in the universe is. Everything rotates, orbits, drifts, streams. Motion is the universal condition. But the motion of our galaxy goes beyond its own rotation and the gravitational dance with Andromeda. The entire local group, the Milky Way, Andromeda, and the roughly 80 smaller galaxies that cluster with them, is moving in a particular direction at a particular speed, about 600 kilometers per second, toward something in the direction of the constellation Centaurus, behind the disk of our own galaxy. That something is called the Great Attractor. It sits roughly 150 to 250 million light years away, and for most of the history of modern astronomy, it was hidden from direct view, tucked inside what astronomers call the zone of avoidance, the 20% of the sky so dense with the Milky Way's own gas and dust that looking through it in visible light is like trying to see across a room filled with smoke. The dust absorbs and scatters the light of anything behind it. The galactic disk hides a significant portion of the sky from us simply by existing. In the 1970s and 80s, astronomers measuring galaxy velocities noticed something that didn't fit. Galaxies across hundreds of millions of light years were all carrying an additional motion beyond the Hubble expansion. A coherent, directed drift pointing toward the same region of sky, toward the zone of avoidance, toward what we couldn't see. The signal was unmistakable. A massive concentration of matter, sitting precisely in the region we were unable to observe directly. Later, X-ray and radio observations, wavelengths that penetrate dust more effectively than visible light, partially revealed what was there. A dense knot of galaxy clusters. The Norma cluster near the center. Other clusters in its gravitational orbit, the combined mass likely in the range of 10 to the power of 16 solar masses, 10 million billion suns, the Great Attractor, and the Milky Way falls toward it at 600 kilometers per second. Every minute you breathe, every day the Earth completes another rotation. We fall. The whole local group, the entire Virgo supercluster, all of it pulled in the same direction by the same gravitational knot, hidden behind our own galaxy's disk. Not dramatically, not in a way that will affect anything in any human lifetime, but falling nonetheless. Laniakea exists only as a direction. In 2014, a team of astronomers led by R. Brent Tully announced they had identified the supercluster that contains the Milky Way, and they named it Laniakea. The word is Hawaiian, and it means immeasurable heaven. Laniakea is approximately 520 million light years across. It contains roughly 100,000 galaxies, including the Milky Way, Andromeda, the Virgo cluster, the Hydra Centaurus supercluster, and dozens of other galaxy groups and filaments. Its total mass is estimated at around 10 to the power of 17 solar masses. It is, in terms of the sheer number of galaxies it holds, among the largest structures that have been given a single name. But what makes Laniakea genuinely unusual, what separates it from every earlier attempt to draw a boundary around our cosmic neighborhood, is how it was defined. They didn't draw the boundary by looking at where galaxies clustered. They drew it by looking at where galaxies moved. Laniakea is defined as a gravitational basin. Every galaxy inside it is flowing, to some degree, toward the same attractor. The boundary of Laniakea is the watershed, the imaginary surface where a galaxy's peculiar velocity tips one way or another, toward this basin or toward a neighboring one. Inside the watershed, Laniakea; outside, somewhere else. This is a profound way to define a structure, not by proximity or density, but by gravitational allegiance, by the direction a galaxy falls. But the watershed is not a sharp line. It is a region of ambiguity, where the competing poles of adjacent basins make a galaxy's allegiance difficult to determine. And newer research, published in 2023, suggests that Laniakea may not be a gravitationally bound structure at all in the long run. As the universe expands, the galaxies within Laniakea may never reach the shared attractor. The expansion could carry them apart faster than gravity pulls them together. The basin may be draining in all directions. What we called home, this immeasurable heaven, may be less a home than a direction of fall. We still don't know how to draw the boundary, and tonight, that's where we'll leave it. Two colliding galaxies produce almost no collision. Picture two galaxies approaching each other, hundreds of billions of stars in each. They begin to overlap. The leading edges interpenetrate. Gravitational tides pull long streamers of stars off into arcing tidal tails. The shapes distort and spiral and stretch. It looks, in simulation and in the photographs of real interacting galaxy pairs, catastrophic, violent, like a collision in the most literal sense. And then, if you were inside one of those galaxies, on a planet orbiting a star caught in the middle of the merger, almost nothing would happen to you directly. The average distance between neighboring stars in our part of the Milky Way is several light years. Proxima Centauri, our nearest stellar neighbor, is 4.24 light years away, and that is the nearest one. The single closest star out of 400 billion. To visualize the spacing, imagine a marble placed in the center of a large city. The next marble sits somewhere on the other side of the continent. That is approximately the proportion, a marble-sized star, and the nearest stellar neighbor separated by a continent of empty space. When two galaxies collide, those marbles pass through each other's grids. The cross-sections are too small, the distances too vast. Even as billions of stars interpenetrate over hundreds of millions of years, the probability of any single star striking another is calculably close to zero. What collides is not the stars. What collides is the gas, the clouds of hydrogen and helium that make up the diffuse interstellar medium of each galaxy. Compressed by the encounter, those clouds heat and ignite into episodes of intense, brilliant star formation called starbursts. In the decades and centuries after galaxies merge, some of the most luminous star-forming regions in the universe blaze to life inside them. The dark matter halos of both galaxies interpenetrate and slowly settle into a new combined structure. The gravitational potential reshapes completely. Stars that were once in stable circular orbits are thrown into eccentric paths, scattered to the far reaches of the merged system, or flung out entirely into intergalactic space as ejected stars. But the stars themselves do not hit each other. The galaxy merges. The stars mostly do not notice. Space is mostly space, even when it is full of stars. 90% of all galaxies are permanently beyond our sight. The number we cite for galaxies in the observable universe, 2 trillion, is already difficult to hold in the mind. 2 trillion, 12 zeros after the 2. But even within the zone we call observable, most of what exists is invisible to us. In 2016, a team of astronomers conducted a comprehensive analysis of Hubble's deep field images and other survey data. The previous estimate for galaxy count, around 200 billion, had stood for years. The revision was by a factor of 10, 2 trillion. The reason for the upward revision was that the early universe was far denser than it is today. Galaxies that formed in the first few billion years were small, faint, and compact. Most of them have since merged into larger structures, the large ellipticals and massive spirals we see today, each one containing the absorbed remnants of dozens or hundreds of smaller precursors. The Hubble deep fields, looking back in time, showed more galaxies than expected at early epochs, but they were at the edge of detectability. Here is the part that's harder to absorb. Of those 2 trillion galaxies, roughly 90% are currently too faint, too distant, or too small to observe with any telescope we have built, including the James Webb Space Telescope. 90%. Not because we haven't looked in that direction, not because we lack the technology to aim a telescope there. Some of these galaxies are simply too faint for any instrument we can currently conceive to resolve. They emit light that arrives here at levels below the detection threshold of our best detectors. Some are dwarf galaxies so small and diffuse that they blur into the background noise of the sky. Others have their light contaminated by brighter foreground objects. The observable universe, the universe we can in principle receive signals from, already contains more than we can see. 2 trillion galaxies, perhaps 200 billion accessible to detailed study, 1,800 billion invisible within the very region we know exists, and that is only inside the cosmic horizon. Beyond the horizon, unknown. The cosmic web was built before the first stars burned. Before any star burned, the universe had structure. In the early moments after the Big Bang, in the first fractions of a second, the universe was almost perfectly uniform. Hot plasma, expanding outward, nearly identical in every direction, but not quite identical. At the quantum level, there were tiny fluctuations in density, random variations, smaller than any scale that means anything to human experience, imprinted on the fabric of space by the physics of the first instant. Those fluctuations were the seeds, dark matter, the invisible gravitationally active component that makes up roughly 27% of the universe's energy content, began to clump along those density variations as the universe expanded and cooled. It does not emit light, does not interact with normal matter, except through gravity, but it gravitates the same way everything else does. And gravity, patient and relentless, began to build. Over hundreds of millions of years, dark matter assembled into a web, a three-dimensional structure of filaments, sheets, and nodes, threaded through with enormous empty voids. Where filaments crossed and thickened into nodes, the gravitational pull was strongest. Gas, hydrogen, and helium, the ordinary matter of the universe, fell along the dark matter scaffolding toward those nodes. And inside the densest regions, after enough gas had accumulated, pressure and temperature rose high enough. The first stars lit. The cosmic web preceded them. The architecture was in place before the first photon escaped into transparent space. The scaffold was built before anything grew along it. Galaxies did not form at random. They formed inside the web, inside the filaments, and at the nodes where filaments converged. The Milky Way sits inside a filament. The local group sits inside a filament. Laniakea is a node where several large filaments converge. The Virgo cluster, the Coma cluster, the Perseus cluster, all of them sitting at the intersections of invisible threads of dark matter, billions of light years long. The web does not glow. It cannot be photographed directly by any conventional telescope, but it holds everything we have ever observed in its quiet, ancient architecture. Every galaxy you have ever seen in any image was placed there by structure older than light itself. The buoy's void has 60 galaxies where 2,000 should be. In 1981, astronomer Robert Kirshner was conducting a survey of galaxy redshifts, systematically mapping the distances of galaxies in different directions, when he found a region of the sky that was almost empty. Not sparse, not underdense by a modest margin, nearly nothing. The buoy's void, sometimes called the Great Nothing, is roughly 330 million light-years across. In a region of that size, the standard distribution of matter in the universe would predict something like 2,000 galaxies. Distributed throughout its volume in the usual pattern of the cosmic web, clusters at the intersections, filaments threading through, modest voids between them. The Bode's void contains approximately 60 galaxies. 60. The interior is so empty that the few galaxies that do exist within it are scattered along its edges and across its face in a pattern that looks, in three-dimensional maps, like a thin foam, a shell of galaxies surrounding a vast central absence. No one is entirely certain why the Bode's void is so empty. The leading explanation is that it formed at the intersection of several smaller voids that happened to align, each one evacuating mass into surrounding filaments over billions of years, their combined absence merging into a single supervoid. The cosmic web, like any large-scale structure, has regions of exceptional density and regions of exceptional vacancy. Buoys landed at an extreme, but the scale of it sits uncomfortably. A single supercluster, a gravitational basin containing tens of thousands of galaxies, would fit inside the Buoy's void with room to spare. If the Milky Way had formed inside it, the nearest other galaxy would have been nearly invisible until the mid-20th century with our best instruments. Astronomers in the 1920s, who were just beginning to realize that the spiral nebulae, or entire galaxies outside our own, would have looked out into the void and found almost nothing. The sky would have contained no hint of the larger universe beyond. Looking out from inside the void, the universe would appear to be mostly darkness, with a faint ring of distant galaxies very far away. We don't know how many supervoids of this scale exist. Probably many. The cosmic web has depths we have barely begun to map. The Andromeda merger is no longer certain. For decades, the collision of the Milky Way and Andromeda was presented as a settled fact about our future. In approximately 4.5 billion years, give or take, Andromeda, currently approaching us at roughly 110 kilometers per second, would arrive. The two galaxies would interpenetrate, their shapes distorting under gravitational tides, long tidal tails sweeping out into intergalactic space. They would pass through each other, swing back together on a second approach, and eventually, after 1 billion or more additional years, merge entirely into a single large elliptical galaxy. The simulations of this event were striking and detailed. The merged result had been nicknamed Milkdromeda. It had been referenced in textbooks and science programs as a settled prediction, a definite future event, as certain as the sun rising. In 2025, a team of researchers led by Til Sawala revisited the trajectory using data from the Gaia spacecraft and the Hubble Space Telescope. These instruments had measured Andromeda's motion with a precision that was not available when the original collision prediction was made in 2012. Andromeda's transverse velocity, its sideways motion, perpendicular to the direct line between the two galaxies, was not well constrained by older measurements. The new data revised that estimate, and the revised numbers introduced a much wider range of possible futures. The probability of a direct merger occurring within the next 10 billion years, approximately 50%. Not 90, not near certain, 50-50. Andromeda may veer. Its trajectory may be more oblique than simulated, producing a near miss that gravitationally disrupts both galaxies and flings streamers of stars into intergalactic space, but produces no merger. Or the encounter may happen later, or differently, or at an angle that produces a glancing blow rather than a full coalescence. The future of the night sky 4 billion years hence, the dramatic double galactic core blazing overhead in those old simulations, is now less written than we thought. The universe does not maintain a fixed schedule. We don't know what will happen, and somehow, sitting with that uncertainty feels more honest than the old certainty ever did. The Milky Way's outer disk bends away from flat. The Milky Way is not flat. This is a recent discovery. Not recent in human terms, not this year, not this decade, but recent enough that the generation of astronomers who established the basic structure of the galaxy did not know it. The spiral arms, the central bar, the thick disk and thin disk, the stellar halo surrounding it all, these were known. The shape of the outer rim was not. A barred spiral galaxy is typically depicted as a smooth, even disk, arms sweeping outward from a bright central bar in a plane that extends consistently across its full diameter. The Milky Way's disk, at our location roughly 26,000 light-years from the center, is about 1,000 light-years thick. Toward the core, it thickens. Toward the edge, it thins out. But the outer disk, the distant rim of the galaxy beyond about 30,000 light-years from the center, is not in the same plane as the inner disk. It bends. Upward on one side, downward on the other, like a vinyl record left too close to a heat source. Not a dramatic warp, not visible to the eye, even if you could somehow stand above the galaxy and look down, but a gradual, measurable departure from flat. The warp was confirmed with precision in 2019 by a team at the Astronomical Observatory of Warsaw, using data from thousands of Cepheid variable stars. Cepheids are pulsating stars whose brightness cycle is directly related to their luminosity, making them reliable distance markers. By mapping their three-dimensional positions, the team traced the shape of the outer disk and confirmed the warp extending to roughly 60,000 light-years from the galactic center. The most likely candidate is the gravitational influence of the Large and Small Magellanic Clouds, two smaller galaxies currently orbiting the Milky Way, whose passage close enough to the outer disk could impart the long, slow distortion we see. Another possibility is the memory of an ancient merger, the structural residue of a smaller galaxy absorbed long ago. We mapped the edge of our own galaxy and found it bent. We still don't know why. Every galaxy we have photographed has already changed. Look at a deep field image. Thousands of galaxies, each one a faint smear of light at a different distance, arranged at different depths across an area of sky no larger than a grain of sand held at arm's length. A galaxy 2 billion light-years away is seen as it was 2 billion years ago. The light reaching us now left that galaxy before complex animals had appeared on Earth, before anything with eyes or a mouth or a nervous system had evolved on this planet. What we photograph is not the galaxy. It is a preserved moment, a fossil of the galaxy, frozen at the instant the light departed. The galaxy as it exists now, after 2 billion additional years of mergers and star formation and gravitational evolution, is invisible to us. Its current light hasn't arrived. It will not arrive for 2 billion more years. Some of the galaxies in those photographs no longer exist in the form we see. They have been consumed, merged, gravitationally reshaped by encounters we cannot observe from here. The small, irregular shapes at the edges of deep field images, proto-galaxies, barely 1 billion years old at the time the light left them, have long since been absorbed into much larger structures. In a deep field image, you are looking at objects that no longer exist as photographed. The image is history, not a map. The James Webb Space Telescope has photographed light that left its source more than 13.4 billion years ago from galaxies that formed within 400 million years of the Big Bang. Those galaxies, if they still exist at all, have been merging, evolving, and changing for 13 billion years since that light left them. Every galaxy we have named and cataloged, we have cataloged its past. We have never seen the universe as it actually is right now. We don't have a way to. Stars are separated by distances that make the galaxy nearly empty. There's a thought experiment that stays with you. Take a ping pong ball. Set it down in a field somewhere. This is the sun. Now drive 2 miles. Get out. Set down another ping pong ball. This is Proxima Centauri, the nearest star to our own. Now do this 400 billion times. 400 billion objects, most separated from their nearest neighbor by 2 miles or more of absolute nothing, spread across a disk so wide that at the same scale it would stretch far beyond any human map. And yet, the galaxy looks dense in photographs. It appears as a luminous band across the night sky. It seems full. What we see is not density. It is accumulation. The combined light of 400 billion suns, each one separated from its neighbors by those 2-mile gaps, adds up over the full depth of the disk to produce something bright enough to see. The individual stars are invisible at this scale. The spaces between them, the vast, quiet, absolutely dark spaces, don't show. Only the cumulative glow registers. Walk through the galaxy in a spacecraft, and you would spend almost all of your time in darkness, an empty darkness broken occasionally, every few years of travel at light speed, by a distant point of light. The galaxy is mostly the dark between, mostly the silence between, and yet the galaxy holds together. Gravity, acting across those 2-mile gaps, accumulating across 100,000 light years, produces something coherent. The disk rotates, the spiral arms persist. The center holds a supermassive black hole that 400 billion objects orbit in a slow, patient, enormous wheel. Order assembled from emptiness, on a scale that takes 100,000 years of light to cross. Dark energy is quietly winning. About 5 billion years ago, something changed in the history of the universe. For the first 8 billion years after the Big Bang, the universe expanded, but the expansion was decelerating. Gravity was doing what gravity does, pulling everything back toward everything else, slowing the outward rush of space. Year by year, era by era, the expansion rate decreased. Then it reversed. Not the expansion itself. The universe kept expanding, but the deceleration stopped. And then, gradually at first, and now unmistakably, the expansion began to accelerate. Something was pushing outward, overriding gravity across cosmic scales, causing space itself to stretch faster with each passing billion years. That something is called dark energy. We don't know what it is. The best formal description treats it as a property of the vacuum, an inherent energy density of empty space, the cosmological constant that Einstein introduced and then famously called his greatest blunder, and which turns out to be real. As the universe expands and creates more space, more of this vacuum energy exists, which drives more expansion, which creates more space. The more space there is, the more dark energy there is. Dark energy currently accounts for approximately 68% of the total energy content of the universe. Dark matter, the invisible gravitational scaffolding holding galaxies together, accounts for about 27%. Normal matter, stars, planets, gas, dust, people, trees, oceans, all the atoms in all the things you have ever touched or seen, 5%. Everything we can observe, photograph, weigh, or touch is 5% of what exists. The thing that is reshaping the entire future of the cosmos, driving the acceleration that will eventually push every unbound galaxy across the cosmic horizon and out of our observable universe forever, is 68% of everything. And we cannot detect it directly, identify its constituents, or explain it from first principles with any theory that feels complete. The acceleration continues. Every year, the rate of expansion increases slightly. The galaxies beyond the local group retreat a little faster, and the universe moves step by step toward a future of isolation, a future where the local group floats in an expanding darkness, surrounded by nothing reachable, all evidence of a larger cosmos erased. The Milky Way falls toward a hidden mass at 600 kilometers per second. There is a region on old star maps called the Zone of Avoidance. The name sounds cautionary, a place marked by cartographers who, unable to see through, chose to label rather than explore. And in a sense, that is exactly what it was. The Zone of Avoidance is the band of sky blocked by the Milky Way's own disk, so dense with gas, dust, and the accumulated light of billions of stars that anything behind it, at visible wavelengths, is simply hidden from view. Roughly 20% of the sky falls within this zone. For most of observational astronomy's history, that band was a blind spot. It was noted, labeled, and set aside. In the 1970s and 1980s, astronomers measuring the peculiar velocities of galaxies, the velocities beyond the expected Hubble expansion, the additional motion caused by gravitational attraction, noticed something that didn't fit. Galaxies across vast volumes were carrying an extra drift. Not random, not chaotic, directed, pointing toward the zone of avoidance, toward the region we couldn't see. Hundreds of millions of light years of galaxies, all moving in the same direction, pulled by something hidden behind our own disk. The mass required to produce that pull had to be enormous, concentrated, dense, sitting precisely in the region 20th century astronomy was least equipped to examine. Later observations in radio wavelengths and X-ray, which penetrate dust far more effectively than visible light, began to reveal what was there. A dense concentration of galaxy clusters, the Norma cluster near the apparent center, other clusters in its gravitational grip, a knot in the cosmic web massive enough to exert a gravitational influence across hundreds of millions of light years in every direction. The Great Attractor. The Milky Way falls toward it at 600 kilometers per second. Not just the Milky Way, the entire local group, the Virgo supercluster, the entire Laniakea basin, all of it in motion, all of it oriented. Every second of every day, we move 600 kilometers closer to something we can still only partially see. The Hercules Corona Borealis Great Wall should not fit in the observable universe. In cosmology, there is a foundational principle called the cosmological principle. It states that on the largest scales, the universe is homogeneous and isotropic, roughly the same in every direction, roughly the same everywhere. Matter, on sufficiently large scales, should be distributed evenly. This leads to a theoretical prediction. There is a scale above which no structures should form. The density fluctuations from the early universe, which seeded all structure, were smooth at large scales. By the time you zoom out to roughly 1.2 billion light-years, the universe should look like a uniform, featureless distribution. Structures larger than that should not exist. The Hercules Corona Borealis Great Wall is approximately 10 billion light-years long. It was identified in 2013 by analyzing the positions of gamma-ray bursts, the most energetic explosions in the universe, luminous enough to be detected across most of the observable volume. In a band of sky spanning from the constellation Hercules to the constellation Corona Borealis. The bursts were not distributed randomly. They clustered in a coherent, elongated structure, stretching across approximately 10% of the entire observable universe. A structure that our best cosmological models say should not have had enough time to form. The homogeneity scale is 1.2 billion light-years. The Hercules Corona Borealis Great Wall is 10 billion. The data remain debated. Some analyses support the signal strongly, others find it weaker. It has not been definitively confirmed as a single coherent structure. The identification depends on the method of analysis and the completeness of a gamma-ray burst catalog. But if it is real, If the universe built something on that scale, then the cosmological principle, one of the foundational assumptions of modern cosmology, needs to be revised, or at minimum, carefully re-examined. A structure the observable universe should not contain. We don't know what to do with that. The space between stars carries a slow archive. The interstellar medium is the name for everything between the stars. Not empty, close, very close, but not quite. At its most diffuse, the interstellar medium contains roughly 1 atom per cubic centimeter. In the densest molecular clouds where stars are forming, it can reach thousands or tens of thousands of atoms per cubic centimeter. By the standards of any laboratory vacuum on Earth, it is almost nothing. By the standards of the space between galaxies, it is relatively rich. It contains hydrogen and helium, the primordial elements produced in the first 3 minutes of the universe's existence, but also everything that has been expelled by dying stars since then. Every supernova that has exploded over the history of the Milky Way has seeded the medium with heavier elements: oxygen, carbon, silicon, nitrogen, iron, sulfur. The medium is chemically enriched, slowly and cumulatively, by each generation of stellar death. Organic molecules have been detected throughout the interstellar medium. Simple ones like water and carbon monoxide, and increasingly complex ones including formaldehyde, ethanol, glycine, an amino acid and building block of proteins, and polycyclic aromatic hydrocarbons. The chemistry loosely associated with biological processes exists at extreme dilution in the dark between stars, not organized into life, scattered, cold, moving slowly through space over millions of years. It carries magnetic fields, filaments of magnetic force threading through the galaxy, aligning dust grains into patterns that polarize starlight, channeling the paths of cosmic ray particles, influencing the collapse of molecular clouds into new stars. And it carries the remnants of every star that has ever died. When a massive star ends in a supernova, it expels its outer layers into the surrounding space at thousands of kilometers per second. That material expands, cools, and merges with the interstellar medium. It enriches the pool from which the next generation of stars forms. The oxygen in the air you breathe was forged inside a star that exploded before the solar system existed. The iron in your blood passed through a supernova shockwave and spent millions of years drifting through the interstellar medium before gravity drew it into the disk of material that became Earth. The space between stars is not empty. It is a slow archive of every star that has ever burned and died. We live in a medium galaxy, in a modest cluster, at the edge of a minor arm. Astronomers classify galaxies by size, mass, morphology, and star formation rate. On every one of these scales, the Milky Way sits somewhere in the middle. It is a barred spiral galaxy, a structure accounting for roughly 65% of all spiral galaxies observed. Its mass is somewhere between 700 billion and 1 trillion solar masses, placing it among the larger members of the local group, but unremarkable by any broader standard. It is not actively forming many stars compared to some younger, more turbulent galaxies observed in the early universe. It is not quiescent and dead like the old ellipticals that have exhausted their gas supply. The local group, a Milky Way, Andromeda, and roughly 80 smaller companions, is not a particularly rich cluster. The Virgo cluster, 65 million light-years away, contains more than 1,300 confirmed galaxies. Our group has about 80. In terms of mass and galaxy count, the local group is a modest structure. The Virgo supercluster, the larger region containing the local group and the Virgo cluster, spans roughly 110 million light-years and holds between 100 and 200 galaxy groups and clusters. Our position within it is peripheral. The Virgo cluster sits near the center. The Virgo supercluster is itself a minor component of Laniakea, a single arm of the larger gravitational basin, not the center, not the densest part. And Laniakea, spanning 520 million light-years, is one of perhaps dozens of comparable superclusters within the observable universe. The Coma supercluster, the Perseus-Pisces supercluster, the Shapley concentration, and others spread through the observable volume. The Milky Way sits at the edge of a medium supercluster, inside a small cluster in a medium galaxy. Not at the center of anything, not the largest example of anything. The middle, in every measurable direction. The afterglow of creation still moves through this room. There is light surrounding us that we cannot see with our eyes. In 1964, Arno Penzias and Robert Wilson were attempting to use a large microwave antenna at Bell Labs in Holmdel, New Jersey, for communications research. Their instrument was picking up a persistent faint noise, a background hiss present in every observation, at every time of day, in every direction they pointed the antenna. They tightened connections. They cleaned the antenna. They found a pair of pigeons nesting in the horn, removed them, cleaned the guano, and checked again. The hiss was still there. It came from everywhere, every direction in the sky, uniform and constant. Nothing in their instrument calibrations could account for it. What Penzias and Wilson had found, accidentally, while trying to eliminate a noise they thought was equipment error, was the cosmic microwave background, the afterglow of the Big Bang itself, the relic radiation from the moment, approximately 380,000 years after the universe began, when the hot plasma of the early cosmos cooled enough for electrons to bind with protons, and space went from opaque to transparent for the first time. When that transition happened, the light that had been trapped inside the plasma for 380,000 years flooded outward in every direction simultaneously. It has been traveling ever since. 13.8 billion years of travel, expanding with the universe, cooling from the fierce heat of the early plasma to the current temperature of 2.725 degrees above absolute zero, barely above the coldest temperature physically possible. Stretched to microwave wavelengths by the expansion of the universe. But here, right now, a few hundred photons per cubic centimeter, passing through your walls, and through this room, and through your body, without interaction, remnants of the universe's first light, threading through everything constantly. The warmth of creation, diluted across 13.8 billion years of expansion, still traveling, still filling all of space, here. Of 4 stars, the universe was hotter than any star's core. We speak of stars as the extreme heat sources of the universe, as the engines that forge the heavy elements, that sustain nuclear fusion at their cores, that burn at temperatures no other environment we can observe can match. The core of the Sun reaches about 15 million degrees Celsius. The cores of massive stars in their final moments before supernova reach several billion. These are the most extreme thermal environments in the contemporary universe. Now step back 13.8 billion years, 1 second after the Big Bang. The temperature of the entire universe, not a star, not a plasma jet, not a nuclear reaction, but all of space everywhere, the entire extent of the cosmos, was approximately 10 billion degrees Celsius. Everything, everywhere, at once. Hotter than the interior of any star that has ever burned or will ever burn. 10 seconds in, the universe had cooled to about 1 billion degrees. At that temperature, the conditions for nuclear fusion existed everywhere simultaneously, not in a stellar core, not in a confined plasma, but across all of space. Protons and neutrons collided and stuck. Helium nuclei formed. In approximately the first 3 minutes of the universe's existence, about 25% of all ordinary matter was fused into helium. The remaining 75% stayed as hydrogen. That ratio, 3 parts hydrogen to 1 part helium, is the same ratio we observe today in the oldest and most chemically pristine stars in the universe. Stars that formed from gas that had not yet been processed through any subsequent cycle of star formation, that still reflect the primordial composition baked in during those first 3 minutes. 3 minutes, and then the furnace cooled. After about 380,000 years, the plasma became transparent, and the cosmic microwave background we detect today was released. Stars came hundreds of millions of years later. They are late arrivals. Before the first star could burn, the universe itself had already been burning. Everywhere, at once, hotter than any star that followed. The oldest stars in the Milky Way predate the Milky Way. There are stars in the Milky Way that are older than the Milky Way. The galaxy, as a recognizable disk structure with spiral arms and a central bar, assembled over a period from roughly 10 to 12 billion years ago. But the stellar halo, the diffuse, roughly spherical distribution of stars surrounding the disk, extending out to 100,000 light-years and beyond in all directions, contains stars considerably older than the disk. Stars that formed in smaller protogalactic fragments before the disk coalesced, and were later incorporated into the Milky Way as those fragments merged. Some of these stars are among the oldest known objects in the universe. The star designated HD 140283, sometimes called the Methuselah star, has been measured at approximately 13.7 billion years old, with an uncertainty range that overlaps with the estimated age of the universe itself, 13.8 billion years. The measurement carries significant uncertainty, and the true age is likely slightly lower. But even at the conservative end of the estimate, this star formed within a few 100 million years of the Big Bang. What it is made of tells the story. HD 140283 contains almost no elements heavier than lithium, almost no oxygen, no carbon, no iron, the elements that dominate the chemistry of stars like our Sun. It formed from gas that had not yet been enriched by supernova. It formed before the first generation of massive stars and lived out their short lives and exploded to scatter heavy elements into the medium. It formed in a universe that had not yet experienced a single stellar death. HD 1402A3 is visible through a small backyard telescope. It sits about 190 light-years from Earth, making it one of the nearest ancient stars we can observe. A dim, slowly evolving subgiant, having long since left the main sequence, burning through what remains of its fuel on timescales that make human time meaningless. The Milky Way assembled around it, long after it had already begun. The galaxy is the newcomer. The star was here first. 1 billion years after the Big Bang, galaxies were 10 times more crowded. The observable universe currently holds roughly 2 trillion galaxies, spread across 93 billion light-years of space. But that reflects the universe as it is now, thinned and stretched by 13.8 billion years of expansion, the galaxies distributed across a volume that was once much smaller. Look at the universe as it was 2 to 4 billion years after the Big Bang, and the galaxy density per unit volume was roughly 10 times higher. 10 times more galaxies per cubic megaparsec. Not just because the universe was smaller. The merger rate between galaxies was dramatically elevated compared to today. Small, compact galaxies, the kind that dominated the early universe, collided and combined frequently. The universe was actively building its large-scale structure. Galaxies were assembling into groups and clusters in real time. It was a more active and more violent cosmos. Starburst galaxies, galaxies undergoing explosively intense star formation, triggered by mergers and interactions, were far more common. The rate at which the universe was turning gas into stars peaked somewhere around 2 to 3 billion years after the Big Bang, then declined. We live in the aftermath, in the quieter later era, when most of the easily available gas has already been processed. And it was a chemically barren cosmos by current standards. The earliest galaxies were made almost entirely of hydrogen and helium. The heavy elements oxygen, carbon, silicon, iron had to wait for the first supernovae. Each generation of stellar death enriched the medium a little more, so that subsequent generations of stars formed from progressively more complex material. The stars of the early universe left almost no direct traces visible to us now. A few of them survive in the halos of galaxies like ours, the most metal-poor stars, dim and old, carrying in their compositions the imprint of a universe not yet enriched. A denser cosmos, a simpler cosmos, one we can only glimpse at the edges of what our instruments can reach. The shape of the universe cannot be determined from within it. The observable universe is a sphere centered on Earth, not because Earth is special or central, but because every observer occupies the same kind of position. You see a sphere of light, whose radius is the distance light has had time to travel since the Big Bang. From any other planet, in any other galaxy, the observable sphere is the same size and is centered on that planet. But the observable universe is not the universe. The universe may be infinite. Current measurements of the geometry of the cosmos, derived from the detailed structure of the cosmic microwave background, constrain the spatial curvature to within a fraction of a percent of flat. A flat geometry is consistent with an infinite universe. but measurements of geometry done inside a finite space can always return flat if the curvature is gentle enough. The Earth looks flat to someone standing on its surface. A cosmologist inside a very large but finite and curved universe might measure perfectly flat geometry and conclude it was infinite, when in fact the universe curves gently back on itself far beyond the observable horizon. The observable universe is 93 billion light-years across. If the universe is finite, it must be significantly larger than that for the curvature to fall below our detection threshold. How much larger? We don't know. Some inflation models predict a universe 23 times larger than the observable sphere. Others suggest much larger still. Others suggest infinite. We have no instruments sensitive enough to measure curvature at scales beyond the observable horizon. We cannot send a signal out and wait for it to return. We cannot compare observations from two different corners of the full universe. The shape of the universe, whether it ends, whether it curves, whether it folds back on itself, whether it has a size, is something we are currently unable to determine. We accept this. We continue observing anyway. Some galaxies will never meet, even if time has no end. The expansion of the universe accelerates. Every moment, the rate at which distant galaxies recede from us increases, not because galaxies are moving through space away from us, but because the space between us and them is growing. The fabric of the universe expands, carrying galaxies apart, the way dots on the surface of an inflating balloon move apart as the rubber stretches. At a certain distance from us, roughly 14 billion light-years, the space between us and a galaxy is already growing faster than the speed of light. Not a violation of relativity. Space itself has no speed limit. But the practical consequence is that light from galaxies beyond that threshold will never reach us, even given infinite time. They are beyond the cosmic horizon, and the horizon is effectively shrinking. Because the expansion accelerates, more and more galaxies will cross the threshold over the coming billions of years. Galaxies currently just inside the reachable zone will eventually slip outside it as the expansion rate increases. The local group, the Milky Way, Andromeda, and their companions, is gravitationally bound. Dark energy affects unbound structures, but gravity holds bound ones. The local group will remain coherent for trillions of years. Whatever happens between Andromeda and the Milky Way, the group survives as a unit. But every other galaxy group and cluster in the universe, every structure not gravitationally bound to the local group, is already separating from us, already leaving, already falling away across the expanding distance. In 100 billion years, any civilization living in the local group would look outward and find nothing but their own galaxies. No Virgo cluster, no Coma supercluster, no galaxy filaments, no evidence of large-scale structure. Just their small island group floating in a smooth, expanding, apparently empty darkness. They would have no way to know what surrounded us now. All the evidence would be gone. The Milky Way drifts inside a river moving toward a distant shore. Laniakea is not merely a boundary, it is a flow. When Tully and his collaborators defined Laniakea in 2014, they did it by mapping the peculiar velocities of thousands of galaxies. The velocities beyond what the Hubble expansion would predict, the additional motion driven by gravity. What they found was not random. It was coherent. Every galaxy within the basin was moving, to varying degrees, in the same direction, toward the great attractor, toward the center of the gravitational watershed. The visualization they produced is one of the stranger images in modern cosmology. Lines of velocity, each one representing a galaxy's drift direction, converging from across the full 520 million light-year extent of the supercluster toward a single basin center. It looks less like a map of galaxies and more like a map of water. All the tributaries feeding a single river, all the flows converging toward a shared destination. The Milky Way is one of those tributaries. The local group is one of those tributaries. The Virgo cluster and its 1,300 galaxies, another tributary. All of them streaming in the same direction, carried by a gravitational pull that operates across scales that make the word large seem inadequate. The river flows toward a shore the expansion of the universe may prevent anyone from ever reaching. The great attractor is itself moving, pulled toward the deeper mass concentration of the Shapley concentration, 650 million light-years away. The river feeds a greater river, and we are in it, right now, moving with it at 600 kilometers per second, every second. The Shapley concentration may dwarf Laniakea. Beyond the great attractor, at roughly 650 million light-years from here, lies the Shapley concentration, the densest known accumulation of galaxies in the observable universe. It was first noted in the 1930s by astronomer Harlow Shapley, who cataloged an unusual clustering of nebulae in that region of the sky. At the time, the full nature of galaxies was only beginning to be understood, and the scale of what Shapley had identified would not become clear for decades. The Shapley concentration contains roughly 25 to 30 rich galaxy clusters, including some of the most massive clusters known. The total mass is estimated at several tens of millions of times the mass of the Milky Way. It is not a single object, but a complex of interacting clusters and filaments, occupying a region of space roughly 300 to 400 million light-years across. And the Milky Way is moving toward it, not just because of the great attractor. Analysis of peculiar velocity fields across Laniakea and its surroundings suggests that the great attractor itself may be partially a response to the deeper pull of the Shapley concentration, that Laniakea's gravitational basin is itself embedded in a larger convergence, and that the river of 100,000 galaxies we call home feeds into a still larger flow. Some researchers have proposed that Laniakea may not be a self-contained structure at all, but an appendage, a tributary of a much larger system centered on the Shapley concentration. If that is true, the hierarchy above the Milky Way has another level we have barely begun to describe. A supercluster inside a larger supercluster. A river inside a deeper river. The mapping has not resolved. Looking at the night sky means looking backward through time. The light from the Andromeda galaxy left its source 2.537 million years ago. When that light departed, Homo habilis had not yet appeared on Earth. The ancestors of modern humans were Australopithecines, walking upright in the grasslands of eastern Africa, using stones, not yet constructing anything. The Pleistocene was beginning. The Arctic ice sheets were advancing. None of the hominids alive in those years would be recognizable to us as human in any sense we typically mean. 2.5 million years through the local group, through the dark between galaxies, one photon after another, faint but intact. It arrives now. It enters a telescope or an eye. When you look at Andromeda, you see a galaxy as it was when your deepest ancestry was still sorting out whether to use a sharp stone or a blunt one. Look further. The Virgo cluster is 65 million light years away. You see it as it was when the mass extinction that ended the non-avian dinosaurs had just occurred. The Coma cluster, 320 million light years distant. You see it from the early Carboniferous, the age of the first forests and the first reptiles. The James Webb Space Telescope has captured light from objects over 13 billion light years away. The first recognizable galaxies, still assembling from the collapsing gas clouds of the early universe. Those objects, whatever they are now, have been evolving for 13 billion additional years since the light we see left them. The night sky is not a map of where things are. It is a map of when things were. Every direction is a different age. Every distance is a different era. The nearest stars, a few light years away, show you the sky as it was a few years ago. The Andromeda galaxy shows you 2.5 million years ago. The most distant objects Webb can detect show you the universe as it was in its infancy. You are reading a record. Every time you look up, 5% of the universe obeys the physics we know. Physics as a formal discipline developed over the last 4 centuries. It has produced tools of extraordinary precision. The Standard Model of particle physics describes the behavior of fundamental particles and their interactions with a predictive accuracy that sometimes reaches 1 part in a trillion. General relativity, Einstein's theory of gravity and space-time, has passed every experimental test devised in over a century of effort, predicting gravitational waves, black hole shadows, the bending of light around massive objects, and the expansion of the universe. These are genuine achievements. They represent some of the deepest knowledge humans have ever produced. But the Standard Model and general relativity together describe approximately 5% of the energy content of the universe. The ordinary matter, the matter that interacts with light, that participates in the strong and weak nuclear forces, that is made of protons and neutrons and electrons, that constitutes every atom in every planet and star and gas cloud we have ever observed, accounts for 5%. Dark matter is 27%. It does not interact with light. It does not appear in the Standard Model. Its composition is unknown. It has never been directly detected. We infer its existence from its gravitational effects. The rotation curves of galaxies, the bending of light around galaxy clusters, the large-scale structure of the cosmic web. It is real. We have no idea what it is. Dark energy is 68%. The cosmological constant in general relativity can accommodate it as a term in the equations, but the term is not derived from any underlying physical theory. The measured value of the cosmological constant differs from quantum field theory predictions by roughly 120 orders of magnitude, one of the largest discrepancies in all of physics. What we understand? 5%. What follows rules we don't have yet? 95%. Physics, for all its precision, operates in a thin slice of reality. Space itself expands faster than light in places, and nothing is wrong. The universe is expanding. The rate of that expansion, the Hubble constant, is measured at roughly 70 kilometers per second per megaparsec. For every 3.26 million light-years of distance between 2 points, the distance between them increases by 70 kilometers per second. At approximately 14 billion light-years from here, a galaxy's recession velocity reaches the speed of light. At 28 billion light-years, it reaches twice the speed of light. This violates nothing. The speed of light is a limit on the motion of objects through space. It says nothing about the expansion of the space they sit in. Space itself is not an object. It does not have a maximum speed. It can expand at any rate without violating relativity. The consequence is the cosmic horizon, a boundary beyond which the space between us and whatever is there expands faster than light can travel across it. Light from a galaxy beyond that horizon, even if it were emitted today, would never reach us. The expanding space between us and it would carry the light backward, not in absolute terms, but in terms of progress toward us, faster than the light could advance. Right now, there are regions of the universe from which light has been traveling for billions of years and will never arrive. They exist. They are real. They contain galaxies, presumably, and stars, and everything else the universe contains. We will never know what is there. Not because we lack the technology, because the geometry of an expanding universe makes those regions permanently inaccessible. The observable universe, the 93 billion light-year sphere, is not the universe. It is the universe as far as signals can reach us. Beyond the horizon, the universe continues. We cannot know how far. Galaxies carry every merger in their structure. Galaxies do not form once and remain static. They grow. They consume. They merge with smaller companions, or with rivals of equal size, and reshape themselves in the process. The galaxy we see in the night sky, or in any deep field image, is the accumulated result of billions of years of collisions, tidal interactions, and absorptions. The Milky Way shows this history in its structure. The Sagittarius dwarf spheroidal galaxy is currently being torn apart by our galaxy's gravity, stretched into a long stream of stars that loops around the Milky Way in a vast arc. Its former members, scattered into stellar streams we can trace across the sky. The process has been ongoing for billions of years. Dozens of other stellar streams have been identified in the Milky Way's halo, each one the remnant of a smaller galaxy or globular cluster that was gravitationally disrupted and absorbed over the history of the galaxy. Each stream preserves a kinematic signature, a pattern of velocities that reveals the orbit of the object before it was consumed. The outer stellar halo of the Milky Way, the ancient metal-poor stars moving in highly eccentric orbits very different from the orderly rotation of the disk, is largely assembled from the absorbed populations of smaller galaxies. Stars that formed somewhere else, in a different galaxy, billions of years before the Milky Way absorbed it. The Large Magellanic Cloud, currently orbiting at roughly 160,000 light-years, shows signs of distortion. The Magellanic Stream, a trail of gas 200 degrees long across the sky, is material stripped from it by the Milky Way's gravitational pull. The galaxy grew by consuming its neighbors. It is still consuming them. What we call the Milky Way is a composite, a layered structure built from dozens of smaller objects over billions of years, each one leaving its trace in the chemistry and kinematics of the stars it contributed. A palimpsest, each layer written over the last, but never quite erased. Everything we know was measured from one corner. Every observation in cosmology rests on an assumption that the universe looks roughly the same from any vantage point, that the physics we observe here applies everywhere, that the constants we've measured in our laboratories, the speed of light, the gravitational constant, the charge of an electron, the mass of a proton, hold everywhere, at every scale, across the full extent of the cosmos. This assumption is well supported, but it is still an assumption. Every measurement we have was made from one position, from one planet orbiting one star in one arm of one galaxy within the single sphere of space from which light has had time to reach us since the Big Bang. We have never made an observation from outside that sphere. We don't know whether the laws of physics vary at scales beyond the observable horizon. Most physical theories suggest they don't, but those theories were developed to explain observations made within the observable bubble, and the bubble may not be representative. We don't know whether inflation was uniform, whether the same process that produced the observable universe we inhabit also produced identical or different conditions in regions forever beyond our horizon. We don't know whether there are domains where the fundamental constants take different values. Some speculative frameworks permit this. The data neither confirm nor rule it out. The cosmological principle that the universe is the same everywhere is the most reasonable working assumption we have. It is the assumption that makes the entire project of cosmology coherent. But it is an assumption. Everything we think we know about the universe at the largest scales is knowledge built from one small corner, generalized outward. The best map we have was drawn from one room. The universe has no record of its own beginning. The cosmic microwave background is the oldest light we can observe. It shows us the universe at 380,000 years old, the moment when the hot plasma of the early cosmos finally cooled enough for electrons to bind with protons, and space went from opaque to transparent for the first time. Before that transition, no light could travel freely. Every photon that existed was immediately absorbed and re-emitted by the dense ionized plasma. The universe was a fog, impenetrable to electromagnetic radiation of any wavelength. The first 380,000 years of history are sealed behind that opacity. We can infer what happened during those years from the physics encoded in the CMB, the density fluctuations, the acoustic oscillations in the primordial plasma, the temperature spectrum. From particle physics experiments, we can extrapolate backward to tiny fractions of a second after the Big Bang. The predictions match the observations across many tests, but none of it is direct observation of the early universe. It is reconstruction, forensic inference from what survived. There is a deeper wall still, beyond approximately 10 raised to the negative 43rd seconds after the Big Bang, the Planck time, the smallest meaningful unit of time in current physics. our understanding breaks down entirely. At that scale, both quantum mechanics and general relativity apply simultaneously. They are not compatible. We have no theory that unifies them in a way that produces testable, consistent predictions. The first instant of the universe's existence, the moment of the Big Bang itself, and whatever preceded or surrounded it, is not merely unobservable. It is beyond the reach of any physical description we currently possess. The universe began in a way we cannot describe. It passed through a state we cannot observe. It arrived at a condition we can see only from 380,000 years onward. The beginning is not lost or missing or misplaced. Gone is a more accurate word. Gone in a way that might be permanent. We continue anyway. We've drifted far tonight. From the Milky Way, vast enough that light takes 100,000 years to cross it, and still a coin against the scale of the observable universe. Outward, through the local group, through Laniakayan's slow gravitational river, past the great attractor's hidden pull, through voids 330 million light-years wide that hold 60 galaxies where 2,000 should be, through walls of structure 10 billion light-years long that our models say shouldn't exist, and finally to the horizon, where space expands faster than light, and the universe continues beyond what any signal from us will ever reach. We moved through a cosmos where 95% of what exists doesn't respond to any instrument we've built, where the oldest stars in our galaxy predate the galaxy itself, where two galaxies can pass through each other and the stars barely notice, where a future civilization may look outward into an empty sky and have no way of knowing what surrounded us tonight. We moved through all of it. And here you are, still part of it. The atoms in your body were forged inside stars that exploded before the solar system existed. They scattered through the interstellar medium, were gathered by gravity into the disk of material that became Earth, were cycled through biology and geology for 4.5 billion years, and arrived here, assembled into something that can look outward at the scale of everything and feel the weight of it. You are not watching this from outside. You are one of the places the universe gathered itself into something capable of wondering about its own scale. That is not a small thing, even against the scale of everything we've crossed tonight. If your eyes feel heavy, let them close. If this felt like home, leave a comment when you wake up. We'd like to know where your mind went tonight. And if you're still here, still drifting, the next chapter is already waiting. The universe will still be here when you wake up. So will we. Good night.